Hey everyone, this is a video to go over part 1 of lesson 6.2. So last lesson we were using integrals to find the area between two curves. Today we're going to use integrals to find volume. So we're going to be calculating volumes using rotation. I have a couple of animations to show you to help you visualize it. The first one we're going to do is the disk method. So you can visualize the shapes we're doing as kind of stacks of pancakes or stacks of disks. And I'm going to write something in that box in a second, but I'm just going to go looking at this first example here, and then I'm going to show you a quick animation, and then we'll write our formula in the box. So let's say we were looking at this function. So I'm going to write over top here, y equals root x. So it looks like this from 0 to 1. And so the area under that curve would be shaded in blue. So we're now going to imagine that this region, this area, is rotated around the x-axis to create sort of this sideways bowl type shape. And we're going to be finding the volume of that sort of sideways bowl. So let me just show you a quick animation to help you visualize how that's happening. So here I have my function in red, square root of x. I'm actually going to rotate from 0 to 9 just so it's bigger and easier to see, but it's the same idea. Okay, and I have a bunch of rectangles there. I'm actually going to increase the number of rectangles so we can see it a little bit better. So those are going to be the disks when I rotate. And here we go. We're going to rotate around the x-axis. Do you see that? And creating this solid 3D shape that looks kind of like a sideways bowl. You can spin it around if you want to have a better look at it. Maybe I'll post the link too so you can play around with these animations and get a better idea for how they work. But let me just do that again, square root of x. And we're going from 0, and I was going to 9. So those rectangles there that you see, we'll do 10. Those are going to be your disks, right? So when you spin it around, spin these rectangles around, you create flat disks, and we're going to be adding up the areas of those flat circular disks. But we're going to imagine there's an infinite number of those. So as you can see, that if you have a small number of disks, the volume is not going to be you're not going to calculate the volume very accurately. But if you have many, many, many disks, you get a much better calculation for the volume. And if you have infinitely many disks, that's when you're using an integral and you're getting the exact volume of that shape. So here's what we're going to do. This is our formula that we're going to use. So the volume of our shapes that are being revolved around the x-axis. So you're going to go from whatever bounds you have, will be defined in the problem. So each disk, right, if you think of a circle, the area of a circle is pi times r squared. So we're going to add up the area of each of those disks from the lower bound all the way to the upper bound, dx, and that'll give us the volume of that shape. And that's it. That's the formula. So it's pi r squared, and then all of those disks added up. That's what the integral is doing. Okay, so what we need to do then is for each different scenario, we need to figure out what the radius is. Okay, so let's look at this example again. So we're looking at the curve y equals x root x, and we're rotating it around so we get this sort of sideways bowl shape. And here in red is one of the disks that are highlighted that you get when you rotate it around, right? So let's just think about what the radius of that disk would be. So it would be the height of the curve at that point, right? It's not saying specifically where along the x-axis it is, but the height of the curve at any point is just equal to root x, right? It's the y value, which is y equals root x, so the radius would be root x. Okay, so no matter where along that curve, the radius of that disk would be root x. And so we can calculate the volume using our little formula. So we've got our radius, the bounds of our integral you can see from the picture, we're going to go from 0 to 1. So the volume will be from 0 to 1 pi times r squared. Remember, that's the area of each disk being all added up. So it's going to be from 0 to 1 pi times, and so the radius for us for every single disk is going to be equal to the height of the curve, which is root x. And before I do that integral, I'm just going to simplify it. So the pi can actually come out because that's just a constant, constant multiple, so we can pull it out of the integral. Root x times, or root x squared, those kind of cancel out and you get x. So it's a pretty simple integral here. So we get pi, and then the antiderivative of x is 1/2 x squared, and we're going to be evaluating that at 1 and 0. So that is pi times 1/2 times 1 minus 1/2 times 0. So it's just 1/2 pi, or pi over 2. So that is the exact answer. So don't round your answers here. They should all have, they're going to all have pi in them. So leave it in terms of pi, leave it as an exact answer. So the volume of this sort of sideways bowl is exactly 1/2 pi. Okay, let's do another example where we rotate around the y-axis instead of rotating around the x-axis. I'm just going to get these lights back on. Hold on. There we go. Okay. Here's another curve. This curve is y equals x cubed. Okay, so that's what is shown. Oops, sorry. That's what is shown here. Y equals x cubed. And our bounds for our rotation are going to be between 0 and 8. Okay, and we're going to be rotating around the y-axis. So let me just show you a little picture of what that looks like. I'm going to undo the rotation here. Oh, sorry, it's just frozen. Let me refresh this. Okay. We're going to be rotating around. Sorry, these animations are pretty intense and they take a lot. The computer is working hard to figure out or to do them, so that's why it's so slow. The screen stops at 6, so I'm just going to go from 0 to 6, but we'll go from 0 to 8 in our actual question. Okay, so you can see the curve here. There's the curve, and I'm going to show you what it looks like when we rotate it around. Okay, so this time our disks are like stacked horizontally on top of another instead of this way. So instead of left to right, they're stacked up and down. Okay, so that shape is sort of, it's this time it's kind of a bowl shape again, but it's just a little bit longer and thinner. Okay. So this time our disc, so what I like to do is just draw the other side. So once it's rotated around, and then I like to draw sort of one disc because I need to figure out what the radius of each disc is. So we'll just draw one disc in there. You should do that every time, and I'll say in a question like whether I want you to draw a disc or not. But you should do that because it gives you a good visual, and then you can figure out what the radius is. Okay, so here's the radius of this disc, right? It's the distance from the center to the outer part of the circle. Ooh, I cannot spell radius. Radius equals x value, right? So the distance from the y-axis to the curve here is just whatever the x value is at that point, right? It's the horizontal distance from the y-intercept, or sorry, the y-axis to the curve. So for our curve, y is equal to x cubed. So if I just rearrange this, just take the cube root of both sides, I can figure out what the x value is in terms of y. So it's going to be cube root y. So this is going to be our radius. okay? So the radius is either x or it's cube root y, okay? And we're going to have these discs stacked vertically. So I'm going to be integrating in y this time. I'm going to integrate from y equals 0 all the way up to y equals 8. So when you're rotating this way, you're going to stack vertically and you're going to integrate in y. So my radius is cube root of y, and my bounds for the integral are from y equals 0 to y equals 8. So my volume is going to be y equals 0 to y equals 8 of pi radius squared dy. Okay, so integrating in y. So that's just something to get used to. When you stack your discs vertically, you're going to integrate in y. When you stack your discs left to right, you're going to integrate in x. Okay, so we got to make sure the radius is written in terms of y. So it would be the cube root of y. I'm just going to write it as y to the power of 1/3 because that's easier to take the integral of. The same thing. I'll pull the pi out because it's a constant. And y to the power of 1/3 squared is y to the power of 2/3. Okay, so let's evaluate that integral. So the power gets bumped up by 1, so it becomes 5/3, and we divide by the power. So that's the same thing as multiplying by the reciprocal. So we get 3 over 5 y to the power of 5/3, evaluated at 8 and 0. Okay, and that's equal to y to the power of 8 to the power of 5/3. I can do that in my head. I think that's 2 to the power of 5, so 32. So it'll be 32 times 3 is 96, so 96 pi over 5. I didn't bother plugging in the 0 part because it's going to equal 0. So again, write your answer as a fraction, exact numbers with pi in the answer, so no rounding. Okay, so 96 pi over 5 is the exact volume when you rotate that curve around the y-axis from 0 to 8. All right, last example. Okay, this is the hardest one because we're going to be rotating about a line that is not one of the axes. Okay, so when we look at our radius, it's going to be a little bit different. Okay, so this time we're going to be looking at this curve y equals x squared. And it's going to be rotated around this line here at y equals -3. So this time our radius is going to be longer than it would be if we were rotating about the x-axis. And we're going to be going from x equals 2 to x equals 3. So I'm stacking my discs left to right. So when I write my integral, it's going to be in terms of x because I'm integrating left to right instead of up and down like in the last example. Okay, so let me draw one disc here. I'm going to draw it perfect and try to draw it as best as I can. 1, 2, 3, 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 4, 5, 6. Okay, so it should look like this. Here's my disc. So this shape is going to look kind of like a bowl, but that's been chopped in half. So you're just going to have the upper part of the bowl. I kind of have shaky hands, so my circles aren't the best. This is going to be my radius here. Okay, so you can see I'm going to split it into two parts using colors here. So this part of the radius would be the y value of the curve. Okay, so from the y-axis to the curve, that's the distance y. And then this part of the radius is always going to be an extra 3 added on, so it's extended. Okay, so this is a bigger shape than you would get if you just rotated around the y-axis or around the x-axis. So my radius is going to be the y value of the curve plus 3. And we have to write everything in terms of x for this integral. So it's going to be this curve, for this curve, y equals x squared. So it'll be x squared plus 3. And my bounds from, okay. So this time my volume equals, I'm going from x equals 2 to x equals 3 pi r squared. So adding up all of those disks, and I'm integrating with respect to x because the disks are going left to right. And in this case, it's going to be 2 to 3 pi, and then my radius was x squared plus 3 squared dx. Okay, so in order to take that integral, I'm going to have to expand that squared term there. I'll pull the pi out as well. So it becomes x to the power 4 plus 6x squared plus 9 dx. Okay, and now I'll do the antiderivative. So 1/5 x to the power 5 plus 2x cubed plus 9x. Yeah, that's right. And evaluated at 3 and 2. I'll just start writing over here because I need a lot of space for this part. So it's 1/5 and 3 to the power 5 plus 2 times 3 to the power 3 plus 9 times 3 minus 1/5 times 5 minus 2 times 2 cubed minus 9 times 2. Okay, so if you want, you can go and plug that all in. I've already done that beforehand, so I'm going to just write the answer. We should always write it as an exact fraction or exact number. So it's 446 pi over 5. I would practice this if I were you, because some students struggle typing fractions into their calculator and getting a fraction answer out. So definitely practice doing that and getting those exact answers. Let me know if you're struggling with that and I will help you, because it's not an easy thing to do that quickly. So practice makes perfect. Okay, so that is the end of part 1. So that was the disk method. In part 2 of this lesson, we're going to be doing something called the washer method. If I were you, I would go and do some of the assignment now. So maybe the first page of the assignment, just to make sure you understand the disk method, and then you can move on to video 2 and we'll learn the washer method.